Cool. So this is the second of the videos I'm going to post today. Obviously, they're in a couple different formats. Doesn't really matter. I don't really care. So the first part was on kinematics. It's pretty long. It's like 25 minutes long. I tried to go through as best I can and review everything that I think is important. If you go look at the questions and there's something you don't see in there, just remember that most of what we're doing has to do with recognizing the pieces and parts of these formulae and how do they fit along with everything. So I'm going to go through in this one, and I have the FRQ in front of me here, and I'm going to kind of go through and tell you what to look for. I'm going to try not to solve everything exactly for you. I'm going to look at both questions and kind of give you a general overview on what to do there. I'll be doing so while looking at some of the formula and making sure that we understand kind of all that together. Cool. So I'm going to pull it up. Cool. So what we see here is there is a cylindrical object, and it is going to be rolling down this incline. You can be watching along with me if you want. I'm sure I could figure out a way to share my screen with you. In fact, I'm sure I could do that with ease, but I don't want to spend the time doing that, so just follow along. We have a cylindrical object going down an incline. Now we know that it's going to be doing so due to gravity. I don't know that matters. We're going to read through everything. Okay. A cylindrical object can roll down an incline as shown above in Figure 1. The incline is slightly less than 1 meter in length. A group of students wants to determine the acceleration of the object while it is rolling down the incline. The students have access to the following pieces of equipment. They have a stopwatch, which can measure it gives you the precision. I'm not going to give you the precision, just you can look at that, okay? So we have a stopwatch and we have a clock. We know that a stopwatch is going to be more precise, right? Now what do we mean when we say more precise? Because precision has a very specific definition when it comes to physics. For us, precision, an instrument is as precise, or its precision is 1/2 the smallest unit that it measures. Okay, so let's say that I have something that only measures in feet. It's precise to 1/2 a foot, because I should be able to tell by looking at it if it is more or less than halfway to one way or the other, right? So if I go to measure something and all I can measure is a foot, I should still be able to tell if it's less than 1/2 a foot or more than 1/2 a foot, and that's kind of what they mean when they say precision. So again, we know a stopwatch is more precise because there are smaller measurements on it, so its precision is going to be a smaller range, right? And then again, you'll see that it gives you all these pieces of info. And so I don't know how I adjusted there. My memory card got full. It does say now that I have 1 hour and 5 minutes, so okay. Hopefully I don't leave all that explanation in there, but if I do, whatever. Anyways. So we have a cylindrical object. It is going down the incline. I have no idea what the last thing I said is. It's not a big deal. I'm going to continue reading the question. We're talking about the precision of these instruments. Cool. So assume the object moves with a constant acceleration as it rolls down an incline. We should be able to do that. Gravity should affect at the same rate as it goes down, right? Obviously, it's going to speed up, but the acceleration, the rate at which it speeds up, will be the same. Now, if we were really covering a really large distance, like elevation-wise, g would change, but a small distance like this, g is not going to change, right? Or at least not to a perceptible amount. Okay. Write an equation that includes acceleration and the quantities that can be measured or obtained from measurements using the available equipment on the list. So, what we're going to do is go to our formula sheet, and if they don't give it to you, you need to make sure you go and review this. I think they're giving you the formula sheet. I can't see why they wouldn't if you go to the formula sheet. That's actually, I'll cover another thing on tomorrow. I'll do a video on all the stuff AP needs you to know in terms of like the test stuff. But formula sheet, okay? So go to the formula sheet. Let's go figure out the equations that have acceleration in them, and then let's figure out which one of those equations can I solve using the pieces. That's going to be relatively easy because they gave us the ability to solve, or to measure 2 things. That's it. We can only measure 2 things, right? All of our measurement equipments measure one of these 2 things, right? Bam! What's the distance I just covered? What's the time I just covered it in? That's it. We had a meter stick and we had calipers. That's both distance, right? We had a clock and a stopwatch. They're both distance. 2 of those things are pretty obvious that we're not going to use them. One of them is too small of a measurement for us, all right? And the other one is too big of a measurement. You can probably figure that one out. Again, I'm not going to solve everything for you. But we go through our formula sheet and we're going to go, okay, I can't measure the velocity. I can't measure the velocity. That's not a thing I can do. So, given that I can't measure what my final velocity is, right? I can make an estimation making these measurements, but given just those pieces of information, I don't have time to measure velocity, but I know what the initial velocity is, right? So given all of that information, there should be an equation that I can solve for that has my position or distance, x, that has time variable, and has acceleration related to it. Bam. Straight up. Easy. Cool. Hopefully you get that. If not, ask me questions. I'll post this stuff later. Hopefully you get that, because that one's pretty straightforward. We just covered all those equations. Make sure you go back and look at it. Remember, time, distance, both of them have to be in there. Cool. And then the next thing it's going to say is to design an experimental procedure and what you have to measure. Okay, so I know that all of my things either measure distance or time. So what do I want to use? I don't want to use things that are unreasonable, right? I want to use the pieces of equipment that are going to measure relative to what I want them to. So go look at the 4 pieces of equipment they gave you. Figure out which measurement of length you're going to use, which measurement of time you're going to use. Awesome. That's it. That's all you need to be able to go ahead and solve for, given the pieces of information that they gave you. Right? So, given the pieces of information that they gave you, solve for one distance, one time, and what piece of equipment did we solve for those with. Right? Let me make sure that I'm not leaving anything out when I look at this. Okay. So when you go through and you're doing experimental design, make sure you tell them what piece of equipment. It tells you that specifically. What piece of equipment do you need? Make sure that you go and explain how you're going to measure these things and how they're related to what you're measuring. I'm going to measure these things using these pieces of equipment to find this thing, and they are related because of this. We did this a lot in our labs, right? It was a lot of like our hypothesis. If we see this, then we should see this because of the relationship in these variables, that kind of stuff, right? Yeah. And again, don't forget, as with any experiment, don't do it once. I know it sounds like a thing that you would go like, oh, they're not going to expect me to remember to say that. You'll get more points every time you do this if you say, do it a bunch of times. Right? So whenever we do an experiment, we want to try to reduce the uncertainty by doing a bunch of trials. Okay? Cool. So let's go up to part C. Part C. It says, what quantities could be graphed in order to give myself the slope? This you've seen in a lot of these FRQ questions. Essentially what they're saying with this question is, I want to find some equation. Let me write this out. Some equation, and you should have done this in the other part. Identify what equation you're using, and then figure out how to set that up to give me essentially a y equals mx plus b. So what they're saying is I should be able to graph one of the variables in that equation on this side, one of the variables in this equation on that side, and then the slope of this line should be able to give me the other piece, right? Here's another way of putting that. What I want is, we know that this is, let me write this out. We know that this is y, we know that this is x, and we know that this is m, and we know that this is y equals mx plus b. Cool. We know that it's y equals mx plus b, right? We know that we have y, we have m, we have x. What we want to do is to find one term in our equation that we can set up as our y, that we measured over here. One term that we can find in our equation to set up as our x, and that'll be measured down here. And so that if I go back and graph these things against each other, that the m, or everything else that's left over multiplied by my x term, is going to be my slope, right? You saw this when we did this in, I think, both of the last 2 FRQs. They had some version of that. We've seen that quite a bit. So for instance, I'm not going to go set up the rest of the problem for you. I want you to select what formula you think these things are related to. Let's take another formula and say, this is from a previous problem, but what's good, kind of the same basic idea, is that we have this equation, t is equal to 2 pi squared m over k. This is from simple harmonics, and we already did this. This question actually already came up. I mean, let's say that we want to put these two things in relation to each other. Let's say they're saying, hey, can we find an equation of t in terms of k, right? T in terms of k that is going to give me a slope where I can find m here, right? Well, what I'm going to do is go ahead and say t is going to be my y. So I say t is over here. And I'm going to go, okay, how do I isolate everything that is multiplied by my k? Well, down here, what I can do is say, I want to graph down here. Over k. Cool. So we have this equation, t is equal to 2 pi square root of m over k. Well, let's say, again, I make t my y, and I make square root of 1 over k my x. Well, everything else that's left over, everything that's multiplied by this term, will be my slope, which gives me 2 pi square root of m, and I can solve for that m because of that, right? And we've seen a lot of problems like that. This is not the problem that is here, because I don't want to give you that formula. I think you should be able to derive that formula for the problem. So you go through there again, you'll be able to see how am I deriving that formula, and then how am I saying what's my vertical and my axis, right? Should be actually pretty straightforward, but just make sure you're going through and doing that. And then it says, how can you use this to determine the acceleration? Well, in this case, hopefully you're coming up with one where acceleration maybe is the slope. That's up to you, right? Obviously, if you have other terms there, just make sure you include that. Okay. Cool. Figure 2C. After rolling down the incline, the cylindrical object rolls across a horizontal surface, then it hits a vertical wall and bounces off the wall with the same speed it had before hitting the wall. Note that during the bounce, the object is in contact with the wall for a time interval that is very small, but not zero. On the dot below, which represents the object during the time it is in contact, draw an arrow shooting the direction of the object's acceleration during the bounce. So in other words, while this thing is in contact with the wall, what direction is its acceleration in? Well, does it continue to go in the direction it's already going? Does it continue to speed up in that direction? If it doesn't, if our acceleration is the opposite direction of our velocity, you pretty much have the answer there. Okay. Part D2. Part D2 says, during the time the object is in contact with the wall, is the magnitude of the acceleration greater than, less than, or the same as while it was going down the ramp? Okay. Takes a little bit of thought process there for part D, but what you're asking yourself is, can I relate the time periods in which they'd make these changes in speed, and which one has the greater change in speed? Right? So ask yourself those two questions and you'll be able to solve that relatively easily. Again, actually, I hope these are the clues that I'm giving you are pretty straightforward. I'm trying not to give you the answer, but in my opinion, those are pretty straightforward answers, right? So yeah, that's the first FRQ. Let's go to the second one. I think it's pretty straightforward also as well. Okay. So the second FRQ, this is a free response question. Show your word for each part of the question. An astronaut holds a rock 100 meters above the surface of planet X. The rock is then thrown upward with a speed of 15 meters per second as shown in the figure. The rock reaches the ground 10 seconds after it is thrown. The atmosphere of planet X has a negligible effect on the air, or on the rock as it's falling. They're telling you there is no air. Just ignore air resistance, just pretend like it's not there. We don't have to worry about it. Cool. I think it's obvious just by looking at this problem. What they're telling us is, can we solve for the acceleration given the amount of time? This is an idea that we covered earlier in the year. When I throw something in the air, it accelerates at the same rate as when it was falling, just opposite of my velocity. So it takes this thing a period of time to slow down, and when it stops, and then it's going to fall back to the ground at that same rate. So all I have to do is figure out how long does it take for me to reach this maximum height, and kind of go from there, essentially. Let's read through the problem, and we'll kind of go about that. Yeah. All right. So it says an astronaut holds a rock 100 meters above the surface on planet X. Cool. The rock is thrown upward with a speed of 15 meters per second. I already read all this. The rock reaches the ground 10 seconds after it is thrown. Has a negligible effect of the rock when it is on free fall. Cool. And then it says again, can determine the acceleration of the rock when it is on planet X. Cool. So what we need to know is, how high does this thing go up in the air? We know what its initial speed is, but we don't know what the acceleration is, right? We do know that this thing goes, how high this thing goes up into the air. Cool. And then once we have figured out how high it goes up into the air, we can figure out how long it takes for it to fall. And the combination of these two things should tell us what the overall acceleration is, right? And there should be a way for us to relate those things to each other. Cool. Actually, you know what? Since we know the entire time in the air, we can do this as if it's a parabola. Okay? So since we do know the entire time in the air, we can do this thing as if it's a parabola, and I'll show you what I mean by that. Cool. So we have essentially this parabola. That's how my height changes over time, and it is, again, not in X direction. Don't think of this thing as going away from the base of the cliff. He doesn't throw it, I don't believe, side to side. I believe it's straight up. Yeah, they're thrown upwards. But we can model this thing as a parabola, as long as we use time as my X direction. Once we recognize that, it should be pretty straightforward to notice that we have an equation that already does that relates Y to T as if T were its X direction, right? It has to be squared because we have it modeled as a parabola. So hopefully that idea itself should lead you pretty quickly to saying like, oh, I actually can solve that using that idea, right? I know the time that it's in the air, and I also know what its starting position is. Its starting position is a positive 100 meters, and it's going to land at 0 meters down. So I actually know quite a few pieces of information here, right? So let's again break down the problem as we see it. We break down the problem. We know that my starting position is, in fact, 100 meters off the ground. Bam! We know that it has an initial velocity of 15 meters per second. And we know that its final position is 0 meters because it's going to hit the ground. And I just changed that to YO, so make sure you notice that. Cool. All right, so YO is 100 meters, velocity initial is 15 meters per second, Y is 0 meters, and we know that my T is 10 seconds. Cool. So this is as much hint as I can possibly give you. Using those 4 knowns and knowing I have one unknown variable of acceleration, there should be one formula that relates all of those things to each other. Cool. How does the speed of the rock when it reaches the ground compare to the speed of the rock when it is thrown up? All you have to do is use logic there. All you have to do is use logic there, okay? So how does this thing compare when it hits the ground as opposed to when you throw it up? So I throw it up, but I'm on a cliff, it comes down, but it misses the cliff that I've thrown at and goes all the way down to the cliff floor. Where do I expect it to be going faster? Okay, cool. Yeah, state your reasoning. Hopefully I don't need to do that for you. Part B, a student wants to know the motion of the rock. How would the motion of the rock be done if it was thrown upward at 15 meters per second, 100 meters above Earth's surface? And a clear, coherent paragraph-length response. Please explain how those differences would change. Okay, so obviously you have to solve for the acceleration here, and then all you have to do is compare that to Earth's acceleration. If Earth's acceleration is greater, it's not going to go as high up in the air, because it's going to slow down quicker, but it'll go faster as it goes down towards the ground, so it should spend less overall time in the air. These are not all of the responses that you need, but these are things to look for in this FRQ. And again, hopefully this is enough to help you out. I'll watch it to make sure that it makes sense to me. I've been trying to watch all my videos, not narcissistically, but to make sure they all make sense to me. That's your FRQ and all of your kinematics section. The next thing I'll be working on is dynamics, and I hope that that makes sense and works for you as well. So just keep up with me, AP Physics. We'll be doing a review all this week for all of these things. This is probably the last video I'll post today. Just keep it up. All right, keep up with me. Appreciate it. If I can turn this thing off.